Okay, you need to be at this part of your notes. It says how to rewrite expressions to reveal the percentage growth and decay. First thing that you're going to do is you're going to write, and this is the 4 type problems, just to let you know. Oh, hold on. Alright, so you're going to write the original function. Then you're going to use the power, excuse me, of a power property to rewrite the exponent. And then you'll evaluate the power, which means punch it out on a calculator, and write it in the form y equals a times 1, and it could be plus or minus r to the t. We're going to look at some specific examples here. So I can flip. First one, rewrite an exponential function. From 2004 to 2010, the number y in millions of songs sold by an online music store can be modeled by that function, where t is years since 2004. Find the approximate monthly percent increase in sales. Now, it says here that t is years, so we're going to have to adjust my exponent here in order to represent monthly. Now, to do that without changing the actual function, I'm going to rewrite this expression. And then with my t, I'm going to rewrite t as 1/12 times 12t. So I'm not changing the exponent, I'm just changing the way that it looks by rewriting it in this way. Because t is in years, and I have to represent this rate, this percent increase, which has to do with this base. I have to represent that in terms of months. So I need to take 1/12 of a year. But because that has to be the same as what I have above, that's why I have to have the 12t there in order to make 1/12 times 12 is still 1. But then this is going to represent per month what's going on. Alright, and then we rewrite this again by using the power property, which is saying if you have 2 powers on top of each other, you multiply them together. So all I'm doing is I'm bringing that 1/12 inside the parentheses here, so that this base now is going to change to represent the monthly increase. I'm going to punch out my new base value, which, let me find a, I'm not sure where. Not sure where my calculator went. Okay, and punch that out. So 1.08 to the 1/12. That gives me 1.006. We'll go 434 to the 12t. Okay, so your percentage increase is going to be that decimal, because if we're going to rewrite it, as you see on the previous page, you need to rewrite it in the form y equals a times 1 plus or minus r to the t. So we're going to break apart the 1 in this decimal. And then this represents the rate. So your monthly percent increase in sales is going to be 0.6434%. Because I know the decimal is 0.006434, but to make it a percent, again, we're going to move the decimal place over twice. Okay. For example 6, the amount A in grams remaining of n grams of the radioactive isotope chromium-51 after T days is given by this function. What percent of the chromium-51 decays each day? Alright, now T days, each day is what we're looking for, so we're not going to have to adjust anything here. So really we're going to pick up, like, from example 5, we're going to pick up in that second step, if you didn't see where I drew the arrow. Alright, so I'm going to rewrite the function. Okay. To find the percent that decays each day, I'm going to separate, so I just have the T, because remember we're trying to get to this expression here, and the exponent in that expression is always just T, so I'm going to separate out the number and make it 1 over 28. The T, that's using the power of power property where we break apart the exponent into the two things that make it up. Then I'm going to punch that out, so 0.5 to the 1 over 28, which gets me that. And then I'm going to rewrite it. So I have 1 minus. Now, to figure out what it's subtracting to get that, if you take 1 and subtract 0.9755, it's subtracting that value. So that's the value we're going to put here. So your percent that decays each day, if we move it over twice, is going to be 2.45% decays each day. Okay. Again, to get that number, even though this is 0.9755, to write it as 1 minus that, like 1 minus that would give me the 0.9755, which is what you want to see. Okay, then for example 7, what annual interest rate is needed for the balance of an account to double every 15 years? We can write it like this. Well, let's use A to represent the amount. We don't know the principal. We just want it to double. Now, if we want it to double, that means the base is going to have to be 2 to represent a doubling situation. And then this every 15 years, we're going to make that 1 over 15 times T to represent every 15 years we want it to double. Otherwise, if we left it as T, what we're saying is it doubles every year. We want it to only happen every 15 years, so we're going to divide that by 15 in order to get that percentage that we would need. Again, we're going to rewrite it by bringing the number 1 over 15 into the parentheses with a 2, so that we just have T on the outside. 2 to the 1 over 15 gives me 1.0473. And then rewriting it, it's 1 plus. There. So my percentage increase is going to be 4.73%. So that would be the annual interest rate needed in order to have the balance double every 15 years. Alright, go ahead and flip your change of base formula in example 3 here. I know that second hour was able to get through example 3, or sorry, yeah, second hour. But this will be another example that you can work through if you're second hour, and if you're third hour, this should be filled out in your notes. Okay, so for example 3, we have this situation. We got log base 3 log base 3 of x plus 4 log base 3 of y minus 5 log base 3 of 2 minus log base 3 of z. Alright, this is a condensing problem. The reason this is a 4-type problem is because we're going to have like fraction within a fraction happen. So we're going to do something with that. So we're going to do the same steps we did before, which since we're condensing, we're going to start with powers and then do multiplication and division. So I'm going to move all my numbers that are powers, which are 3, this 4, and this 5, back to being exponents. Okay. Next step would be to multiply, or combine your multiplications. So that's only these first 2 terms. Okay. And now we have 2 divisions going on. Now, with multiplication, it's a little bit easier when you have multiple multiplications going on, because you just combine them all into one argument. But in this case, when you have 2 subtractions going on, what's divided by what? Like, do I move right to left or do left to right? You always move left to right. So we're going to deal with the first division, and then we're going to deal with the second one. So I'm going to combine this and this into one term by dividing. And the same thing, I'm going to deal with the second subtraction sign, which means division again, and divide again. Now when you do that, you get log base 3 of x cubed y to the 4th over 2 to the 5th over z. Okay, so what you have going on here is really a fraction divided by a fraction. And when you have a fraction divided by a fraction, you take the bottom fraction, you flip, and you multiply. So we're going to multiply this one by 1 over z. So your final answer will be log base 3 of x cubed y to the 4th all over 2 to the 5th, which you could write, I think it's 125. Oh, I'm saying 5 to the 5th. Or 5 cubed, sorry. Anyway, 2 to the 5th is 32, so you can write it as 32 if you want, times z. Okay. And the change of base formula. Now this is still dealing with logs, but as we discussed in a previous video, the buttons on your calculator, the log button here, log, represents if you have a base that is 10, because that's common log, because our number system is based on multiples of 10. And then ln is when your base is e. If you don't have a base of 10 or a base of e, you can't use the buttons on your calculator. It won't punch out log base 3 or log base 5. So this formula is when that comes into play. And if you have an expression where the base is not e or 10, you can punch the value in your calculator by using this ratio. For example, log base 3 of 4. Okay, that's a base 3. I can't plug it into the calculator unless I use this formula. So I'm going to do ln of 4 divided by ln of 3. And it gets me that value, 1.2618. Okay, so this change of base formula is really going to come into play for us, when we solve equations, coming up here in a little bit, and when we graph, which is the next section that we're going to be dealing with. And let me quick look at the time. Okay. And I think we'll have time to do at least the steps to graphing. So go ahead and flip. Alright, standard G2. I can graph log functions and determine the domain and range. This includes functions of different bases other than 10 or e. Alright, your steps to graphing log functions are going to look very similar to what we've had before. Before we get to that, the standard's focus is graphing log functions, and one of the key things to pay attention to is the base of the log function. That value determines important things about making your table of values, so you do need to pay attention to it. Alright, the first thing that we always do when we're graphing is labeled transformations. You're going to see H and K up here again, so it's going to move your graph the same way as all the other times we've used it. And the next step is we make a table of values. Now, we are not going to use -1 and 0 and 1 because with an exponential graph that grows very quickly, that gives you 3 points that are kind of spread out. But with a function that grows very slowly, like a log, we want to pick these are far apart, because if we picked 1 and 2, let's say, and we plug those in, then it's going to, there's not going to be much of a difference. Like, you're not going to be able to see much of a curve because it's not going to be much bigger at 2. So we're going to select just 1 and 10. To make our table of values. Key thing here when you make a table of values, you need to make sure to use the change of base formula if needed. And where it's needed is if the base is not 10 or E. Okay, and your last step is to plot the points. Shift, draw in your vertical asymptote, and give your domain and range. Okay. And then I think that's where we'll end today, because I don't want to go over too much. So that'll set us up, and really graphing is going to be fairly simple for you guys to do since you're comfortable with exponentials. So I think this week we'll have, looks like 2 more videos, and then we'll be done with your unit, and we'll be practicing getting ready for our test next week. This is Crisscross signing off.